Morning class. This is day 15 of Coronachem. We're going to continue with the ideal gas law. I'm going to show you how to derive the units for it, and then we'll do a few practice problems. So I left off yesterday with the ideal gas law, which was a combination of four ideas: the effect of pressure upon gas, volume, temperature, and the amount of gas. And then we have the value R to coordinate all the units that we're using so that they work together. Typically when you do ideal gas law problems, you'll use liters and atmospheres. That's the most popular way of doing the calculations. And when you use liters and atmospheres, the value of R is 0.082057. So let me first show you what the Avogadro's number of gas molecules at standard temperature and pressure. That's an important concept. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure. So all gases, all ideal gases, occupy a volume of 22.41 liters under those conditions. So at a temperature of 0 degrees Celsius, 1 atmosphere's pressure, and if you have 1 mole of gas, the volume, according to the ideal gas law, PV equals nRT can be rearranged to isolate for V, so you'll put the P in the denominator. And if you plug in all the values, 1 mole of gas, value of R is 0.082057 liter atmospheres per Kelvin mole, and the temperature of 0 degrees Celsius is 273.15 Kelvin, and the pressure of 1 atmosphere. The volume of all gases, of all ideal gases, will be 22.41 liters. So standard temperature and pressure also known as STP, which happens to be the brand name of the famous motor oil, if you ever wonder where they got that inspiration, is 273.15 Kelvin. And a pressure of 1 atmosphere. If you look at the Give It Some Thought on page 409, it says, how many molecules are in 22.41 liters of an ideal gas at STP? Well, I just finished telling you that if you have 1 mole, first of all, you know that if you have 1 mole of anything, you're going to have 6.022 times 10 to the 23 items. And because we used Avogadro's number for chemistry, 602 sextillion, that's 602 with 21 zeros after it. It's a very big number, but why do we use such a big number? Because molecules are very small, so you need to have that many of them to have even an amount that you can see with the naked eye. If you took, for example, 602 sextillion carbon atoms, you would get 12 grams of carbon. That's about the weight of 3 or 4 pennies. So atoms clearly are very small. So the answer to the Give It Some Thought on page 409 is that you would have 6.02214,086 times 10 to the 23 molecules of gas at STP, standard temperature and pressure. Now let's use the ideal gas equation in a typical problem. So the problem on page 410 of the textbook asks, tennis balls are usually filled with air or nitrogen gas to a pressure above atmospheric pressure to increase their bounce. if a particular tennis ball has a volume of 144 centimeters cubed and contains 0.33 grams of nitrogen gas, what is the pressure inside the ball? All right, so we're going to set it up as an ideal gas problem. We're going to say pressure times volume is equal to the number of moles times the gas constant times the temperature. So if we want the pressure, we'll say P is equal to nRT over V. And then we can plug in the values. The value of N is the number of moles. Well, we have nitrogen gas, and there's 0.33 grams of it. Nitrogen gas has a molar mass of 28.0134 grams per mole. So dividing grams of the substance by the molar mass is going to give you how many moles of the substance you have. Gas constant is 0.82057 liter atmospheres per Kelvin mole. And the temperature in this case happens to be 273 plus, is it 24 or 25? It says 24, okay. 273.15 plus 24 degrees Celsius. So that gives you the Kelvin temperature. All of that over the volume of the ball, which happens to be 0.144 liter. When you plug all that into your calculator, this is the answer you get, 1.9946. 9728. Or, because you're only allowed 2 sig figs, there's only 2 significant figures in that answer, you're going to round it to 2 atmospheres. So the pressure inside of a tennis ball is about 2 atmospheres. So the ideal gas law, PV equals nRT, can be used to calculate the parameters for one set of conditions. Sometimes, though, you have 2 sets of conditions. You might have an initial set of conditions and then a final set of conditions. So that creates a complication. You could use the PV equals nRT twice, and that'll give you the answer. That's fine. Or you can factor out the parts that remain the same and set the equation equal to each other. Because it's equal to a constant, you can set the equation equal to the constant, and you'll have an initial set of conditions and a final set of conditions. They both equal the constant because R has to be there. So let me show you how that works. So we know that PV equals nRT. Well, then that means that PV over RT over NT is equal to R. But R is a constant. So you can have a set of initial conditions, and you can have a set of final conditions. R is invariant, so you can use the ideal gas equation twice to solve for before and after. And that's what we call the ideal combined gas law. And it looks like this. P1V1 over N1T1 is equal to P2V2 over N2T2. And if anything in that equation stays the same before and after, you just cross it out, because mathematically you have the same number. You can just cross out numbers that are the same without affecting the value of the equation. Let's look at a problem where that kind of equation comes in handy. This is on page 412 of your text. Oh, I saw, there's a question on page 411. We'll come back to that one. So 412, it says, a large natural gas storage tank is arranged so that the pressure is maintained at 2.2 atmospheres. On a cold day in December, when the temperature is minus 15 Celsius, the volume of the gas in the tank is 28,500 feet cubed. What is the volume of the same quantity of gas on a warm July day when the temperature is 31 degrees Celsius? So we're going to use the ideal combined gas law. P1V1 over N1T1 is equal to P2V2 over N2T2. Kind of rolls off the tongue. We'll just leave that there for now. At you'll notice that in this problem, it says that the pressure is kept constant. The pressure is maintained at 2.2 atmospheres. So the P can cancel. The P is not going to change. So just cancel it out of the equation. Also, the amount of gas in the storage tank remains constant because it says what is the volume of the same quantity of gas. So the number of moles of gas also stays the same. So we can cancel the N1 and the N2. So basically, our ideal combined gas law for this problem reduces down to this. V1 over T1 is equal to V2 over T2. And now let's see what we are given by the problem. We're told that the volume of the gas initially is 28,500 feet cubed. Now, I know some of you are going to say, oh, what? Lassie, that's not an SI unit. That's okay, because we have an initial condition and a final condition. As long as you're consistent with the units, you'll get the right answer. But don't put feet cubed on one side and meters cubed on the other side. It's got to be the same unit on both sides of the equation. So as long as you're consistent, it's okay. So temperature is minus 15. We're going to add 273 to it to convert it to Kelvin. Final volume is what we're looking for, and the final temperature is 31 Celsius. So again, add 273.15 to convert it to the absolute temperature. When you solve that, well, okay, I'll write another intermediate stage of the calculation to show you what it looks like. When you solve it, you're going to get this. So you can cross multiply. So 258.15 K times V2 is going to give you 28,500 feet cubed times 304.15 K. Solve for V2, and you get by dividing, transposing that 258 on the bottom there. And what you get is 33,578.44 feet cubed. Now, I'm not going to report that number because there's too many sig figs. You're going to report three significant figures, so you get 3.36 times 10 to the 4 feet cubed as your final answer for that question. The units, again, do not have to be SI as long as you're consistent on both sides of the equation. Normally, though, when you do these problems, it's not a bad idea to go back to an SI unit when you report the final answer, just to be compliant with the world, because the world is switching over to a metric system. And of how would we convert? How would we convert 3.36 times 10 to the 4 feet cubed? This is chapter 1 stuff, but let's see how much of it you remember. You're at 3.36 times 10 to the 4 feet cubed, and you want to convert to, I don't know, liters. Let's go to liters. That's the SI unit, or actually meters cubed is the SI unit. So let's start from there. We have 3.36 times 10 to the 4 feet cubed, and you want to go to meters cubed. There's a number of ways you can do it, but I'll show you what I do. Feet has, a foot is 12 inches. But remember, we're doing this in 3 dimensions, so you got to convert, the unit also has to be raised to the power of 3. And then so that allows you to cancel feet. I'm not canceling things that are not the same here. Notice feet cubed and feet. That's not what I'm canceling. I'm canceling feet cubed with feet cubed. How is this feet cubed? There's a cubed over here. That cube distributes to the 12, to the inches, to the feet, and to the 1. So if I was to expand this, I would get 1,728 inches cubed per 1 cubed, which is still 1 foot cubed. So that's what I'm really doing here. So the feet, it's okay to cross it out because it does in fact cancel. All right, continuing though. I want to get rid of inches now, so I'm going to say there's 2.54 centimeters per 1 inch. Again, 3-dimensional because it's a volume. That allows me to cancel inches cubed. And then for centimeters cubed, 1 milliliter is the same as 1 centimeter cubed. And finally, there's 1 liter per 1,000 milliliters. So I can convert it to liters. Or if I want, I can go to meters cubed. There's 1,000 liters. There's 1 meter cubed per 1,000 liters. So if I want, I can go to meters cubed. That's not a bad idea. So let's do that. See what we get. So we got 3.36 exponent 4 times 12 cubed. Where's the cube? Where did they put it? Right here. I don't bother with the 1 because if I cube 1 I still get 1, and dividing by 1 I still get the same number. So I just look at the numbers that actually have an effect. So I'm going to say times 12 cubed times 2.5 cubed, 2.54 cubed. Here I'm just canceling centimeters cubed to go to milliliters. Milliliters cancel. I'm going to divide by 1,000, not multiply by 1,000. You guys do it all the time. You divide by 1,000, okay? See, this times 1 over 1,000 means you divide by 1,000. Okay? I know there's a multiplication sign there, but when the number's in the denominator, you're dividing, okay? Oh, I did it twice here. 1 liter per 1,000 milliliters. Oh, no, I didn't. It's okay. Then I have to divide 1,000, and the liters cancel as well. Yeah. Okay, so the final answer. Where am I? 12 cubed times 2.54 cubed divided 1,000 divided 1,000. Answer. You get 9.51446,045 times 10 to the 2 meters cubed. Or you could say, we're only allowed 3 sig figs, so you say 951 meters cubed. Okay, that's just a little review from chapter 1, which you should know. And since we're doing gases, you should brush up on that a little bit. You can watch a couple videos in the playlist for chapter 1, unit conversions, if you're feeling rusty. Let's go to 413. We'll do the next one. Practice example. It says a 0.5 mole sample of oxygen gas is confined at 0 degrees in a cylinder with a movable piston, such as shown in figure 10.12. The gas has an initial pressure of 1.0 atmospheres. The gas is then compressed by the piston so that its final volume is half the initial volume. The final pressure of the gas is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? A lot of this stuff, we see this in textbooks, a bunch of calculations that have no connection to reality for us living in the 21st century. But all of this stuff was very important in the early stages of the development of both the steam engine and the internal combustion engine. So all one dovetailed into the other. But all through the 19th century, we had steam engines. We would burn coal, boil water. The boiling water would get hot enough so that it would produce very hot superheated steam, and they would use that to drive pistons. They would fill a cylinder with the hot steam, and that would, if it was pressurized to a high enough pressure, it would drive the steam engine. And they got really good at making engines that could extract as much energy as possible from this hot steam. They would have engines that would even recycle the hot steam that came out of the engine and pump it into another set of cylinders. In fact, they had double, triple, I think even quadruple expansion engines where they would recycle the superheated steam, and they would get progressively larger pistons to be able to extract the mechanical energy out of the hot steam. The Titanic was driven by steam engines. Did you know that? We think of it, it was the most modern ship of its time. And it had it was triple or quadruple expansion engines. So there were a bunch of men down in the hold of the ship shoveling coal. That's called stoking. They're shoveling coal into the burners. The burners were under the boilers. The boilers would heat up the water. Then the superheated steam that resulted was used to drive the giant engines of the Titanic. So they were steaming along at 21 knots, which is an amazing achievement for the time. Only, within that decade, they were already developing the internal combustion engine, where they did away with steam and they would just burn fuel inside the piston to cause the engine, the cylinder to expand, hence the name internal combustion engine. So there's a whole lot of thermodynamics that developed around this concept of making engines more and more efficient. And it involved the expansion of gases within a cylinder. And engineers were always looking for ways to maximize the efficiency. An engineer worth his salt is somebody who maximizes efficiency. That's all what engines are about. Trying to increase the amount of mechanical energy that you can derive from the burning of fuel. And we've gotten to a pretty good level. You know, I think cars like the Bugatti Veyron that can generate 1,500 horsepower from an engine, you know, that would probably fit inside a refrigerator-sized volume. So what an amazing thing that we've come so far. There are dragsters nowadays that can generate 11,000 horsepower from an engine that you could hug with your arms open wide. Think about that. You know, how much power is being extracted from fuel. So a lot of science goes into that, a lot of technology, and it's a wondrous thing. And it's also an interesting thing to study. Anyway, getting back on track here. We're on page 413. So we have a 0.5 mole sample of oxygen confined at 0 degrees in a cylinder with a movable piston, such as that shown in figure 1012. The gas has an initial pressure of 1 atmosphere. The gas is then compressed by the piston so that its final volume is half the initial volume. The final pressure of the gas is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? So let's set up our ideal combined gas law. Now, let's try to eliminate anything we don't need. The amount of gas is unchanged in this problem, so N1, and N2 is not going to be needed because the number is going to be the same. Also, the volume. All we know about the volume is that it's half the amount after the piston moves. So let's call the volume 2x at the beginning and 1x at the end. So let initial volume equal 2x, final volume equals x. Okay, so this equation reduces down to P1 V1 over T1 is equal to P2 V2 over T2, and we can plug in the numbers now. The pressure initially is 1 atmosphere, and the volume is initially 2x. We don't know the actual volume. And the temperature is 0 degrees Celsius, so 273.15 Kelvin. And after the piston moves, the pressure is 2.2 atmospheres, and the volume goes down to x. Sorry about the lack of space. And then the final temperature is what we're looking for, so we retain the variable T2. So if you cross multiply, you get 2 T2, because the x's will actually cancel. And it equals 273.15 K times 2.2 atmospheres. So T2 therefore is 300.465 Kelvin. Now if we subtract 273.15, it can come back to Celsius, and that equals 27.315 Celsius. We can't report it to more than 2 sig figs, so basically we're stuck with reporting 27 degrees Celsius as the final temperature using our ideal combined gas law. Now there's a few problems that you're going to get where they're going to ask you to calculate the density of a gas. Just be aware that gas densities are about 1,000 times lower than liquid densities. So for example, water has a density of about 1 gram per milliliter, or if you want 1 kilogram per liter, or if you want, you could say 1 ton per meter cubed. Water has the same density, right? But you can have larger amounts of water or less amounts of water. So if you had a 1 meter cube of water, that would weigh a ton. Here's a quick question. How many grams are in a ton? My students should be able to answer that almost immediately. You know that a ton is 1,000 kilograms, and that 1 kilogram is 1,000 grams. So if you have 1,000 kilograms in a ton and you have 1,000 grams in a kilogram, 1,000 times 1,000 means there's 1,000,000 grams in a ton. So I was saying the density of air is 1/1000th the density of water. So typically the density of air is around 1.2 grams per liter of air. So in problems where density is introduced, it is useful to make an assumption such as 1 liter of gas or 1 mole of gas to aid in framing the calculation. So there's nothing wrong with you pretending a set of conditions. You're not making up numbers, you're just making up a set of conditions, and then allows you to set the parameters for the problem and to solve for the problem. So let's see an example and you'll see what I mean. On page 415 of your text, it's going to ask you to calculate the average molar mass of dry air if it has a density of 1.17 grams per liter at 21 degrees Celsius and 740 torr. So we're told the air density is equal to 1.17 grams per liter at 21 degrees Celsius. Also, be careful of, sometimes in science problems they throw in extra data and students will be mystified because they don't know what to do with a certain number. It can happen. They give you data that you don't need. You have to know your material well enough that you can ignore extraneous information. That's an important skill. It's an important skill more than in just science. It's also important in life. So to make this easier on ourselves, let's pretend we have 1 liter of air. Assume a 1 liter sample of air. Okay, so we're going to use the gas equation, the ideal gas law, PV equals nRT, and we're going to solve for the amount of moles. So we can say N is equal to PV over RT. I'm just transposing the R and the T over, right? Or dividing both sides by RT, whatever works for you. I don't want to split hairs. So you see that's how you cancel the RT. So you get 740 over 760 of an atmosphere. Volume is 1 liter because you assume that. The gas constant when you have liters and atmospheres is 0.082057 liter atmospheres per Kelvin mole. And the temperature is 21. So add 273 to that so that you are using the absolute temperature scale. All these problems have to be done using the absolute temperature scale, which goes to all the way to 0. And when you get to 0, which is 0 Kelvin, not 0 Celsius, 0 Kelvin means there's no more energy, no more heat in the object. So the value of N, when you plug all these numbers into your calculator, is 4.03397,906 times 10 to the negative 2 moles of air. But wait, there's more. Therefore, molar mass is going to be the number of grams in 1 liter, right? Because the density of air is usually described in grams. There's glare here. Sorry about that. Grams per liter. So we had a 1 liter sample, and we also found out that there's that many moles in a 1 liter sample. So if you have that many grams for that many moles, that's grams per moles. Grams per moles, guess what, is the units of molar mass. So divide by 4.039, etc., times 10 to the minus 2 moles. And what you get is that air has an average molar mass of 29.003621. And we'll report it to the correct number of significant figures, which is 3. So you're going to say 29.0 grams per mole. And Bob's your uncle. Let's look at give it some thought. On page 414. What is it asking here? It says in give it some thought on page 414. Is water vapor more or less dense than nitrogen under the same conditions of temperature and pressure? Well, water is composed of H2O, which has a molar mass of 18.0125, 18.01528. Whereas nitrogen, which is a diatomic gas, is twice 14.0067. So nitrogen gas has a molar mass of around 28, whereas water is only 18.01528. So it is less dense. Water has a molar mass of 18, diatomic nitrogen is 28. So since according to Avogadro's law, equal volumes of gases at the same temperature and pressure contain equal numbers of molecules, we can assume 1 mole of gas, and we'll see that the 1 mole of gas, 1 mole of nitrogen would weigh 28 grams, 1 mole of water would weigh 18 grams. And since they occupy the same volume at the same temperature and pressure, then it stands to reason that the nitrogen gas is higher density. So as it turns out, you know, when air has high concentration of water vapor, it's actually less dense than dry air. If you ever drive an old car, I used to drive an old Honda Accord, a 1976 Honda Accord, and I used to drive to college in the mornings, especially on the cold mornings. I noticed my car had a lot more power. Why? First of all, there was no fuel injection, there was no computer-controlled fuel injection in those cars. It was just a straight carburetor going into the engine. So you got what you got. So on a cold day, the air had more oxygen in it because of the lower temperature. There's more air molecules per cubic centimeter. So you had more oxygen to burn the fuel. The engine ran better and had more power on cold days. On a warm, muggy day, the car had an obvious loss of power. Nowadays, they have a computer-controlled fuel injection, so the engine will have different mixtures injected into it according to the climatic conditions and the energy, the oxygen content of the air. So you probably wouldn't notice any loss of performance nowadays. So let's do one more, and then we'll call it a day. This is on 414. It says the mean molar mass of the atmosphere at the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. The surface temperature is 95 Kelvin. That's pretty cold. And the pressure is, 95 Kelvin is about, let's see. It's 178 below zero. Right? Yeah. So it's colder than the temperature of liquid nitrogen. Nitrogen liquefies at a negative 196. So if you're standing on the surface of Titan, nitrogen would become ice. So the surface of Titan is probably covered with things like frozen water, frozen ammonia, frozen nitrogen, and it's otherworldly, literally. So they're asking us to find the density of the gas under these conditions. So the mean molar mass of the atmosphere at the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. The surface temperature is 95 Kelvin, and the pressure is 1.6 atmospheres. So if this is true, then the pressure on the surface of Titan is higher than the surface pressure of the Earth. Interesting, but it's not much bigger than our own moon. Assuming ideal behavior, calculate the density of Titan's atmosphere. Presumably, the very low temperatures in that part of the solar system allows the weak gravity of such a planet, of such a moon, to hold on to an atmosphere. On a place like the Titan, you could use water as a construction material. You know, you could freeze it, blocks of ice, make bricks out of it, and build houses out of ice. Mind you, they'd have to be airtight because there's no air to breathe. All right, so practice example, page 414. We're going to use PV equals nRT. And we're going to solve for volume. nRT over P. We're going to plug in all the conditions on the surface, and we're going to find out what the volume is. We're going to assume 1 mole of gas. That's going to make it easier for us to solve the problem. Let's pretend we have a 1 mole sample of the air on the surface of Titan. I forgot to say that. So assume 1 mole of gas. Assume 1 mole of gas. Okay? So this number is going to be 1. You can assume any number you want, but 1 makes it easier. So 1 mole times 0.082 057 liter atmosphere. They're going to scrunch it in there per Kelvin mole. And then the temperature is 95 Kelvin. And the pressure is 1.6 atmospheres. When you solve the volume of that gas, you get 4.87 liters. So under those conditions, 1 mole of gas, any ideal gas, will occupy that volume. Now, they tell us that the density of the gas is, they tell us the molar mass of the gas is 28.6. So we assumed 1 mole, so we know that we have 28.6 grams. So if we say density equals mass over volume, and we know that the mass is 28.6 grams per mole, and we know that it occupies a volume of 4.87, etc., then the density of the atmosphere on Titan is 5.87011.724 grams per liter, or 5.9 grams per liter is what we're allowed to report, because we only had 2 sig figs on the 1.6. So here's what you can do. Since you don't have the textbook, I'll let you look at the 1 page here at the back, so you can try the next problem, which is, there was one I left undone. This is on page 411 at the bottom of the page. See if you can read that. Okay, try to do that practice exercise, and we'll talk about it tomorrow. I'll read it to you just in case you couldn't get it clearly. It says, the gas pressure in an aerosol can is 1.5 atmospheres at 25 degrees Celsius. Assuming that the gas inside obeys the ideal gas equation, what would the pressure be if the can were heated to 450 degrees Celsius? Okay, so try to solve that. See you tomorrow.